Cosmic rays are high-energy particles that originate from space and interact with Earth's atmosphere, producing a cascade of secondary particles. Discovered in the early 20th century, they represent an important source of information about high-energy physics and astrophysics. Their origin, composition, and the effects they produce on Earth and in space are the subject of numerous scientific experiments. Cosmic rays have different origins and can be divided into two main categories. Primary cosmic rays. These are particles that arrive directly from interstellar space. They can originate from the Sun, solar cosmic rays, supernovae, active galactic nuclei, or even extragalactic phenomena. Their energy can vary enormously, with some particles possessing energies millions of times higher than those achievable in the most powerful terrestrial particle accelerators. Secondary cosmic rays. These are formed when primary cosmic rays interact with the upper layers of Earth's atmosphere, generating a cascade of particles, such as muons, neutrinos, pions, and other subatomic particles. These secondary particles can reach Earth's surface and even penetrate deep into materials. Primary cosmic rays are mostly composed of protons, about 90%, helium nuclei, about 9%, and to a lesser extent, heavier nuclei and electrons. Among the heavy elements, traces of iron, carbon, and oxygen can be found, providing clues about their astrophysical origins. The high energy of cosmic rays suggests that they are accelerated by powerful magnetic fields and extreme astrophysical phenomena. The main acceleration mechanisms include supernova shockwaves. Stellar explosions generate shockwaves that accelerate particles to relativistic speeds. This process is considered one of the primary sources of medium-energy cosmic rays. Relativistic jets from black holes and active galactic nuclei. Strong magnetic fields near supermassive black holes can accelerate particles to extreme energies, even higher than those from supernovae. Shockwaves in stellar winds. Interactions between stellar winds can provide the necessary energy to accelerate cosmic rays, especially in binary systems with massive stars. Interactions in galaxies and galaxy clusters. In environments with strong magnetic fields, cosmic rays can undergo further acceleration during their journey through the universe. When cosmic rays collide with Earth's atmosphere, they produce showers of secondary particles that can be detected on the ground. Some important effects include electronic interference. Cosmic rays can affect the electronic circuits of satellites and aircraft. Cosmic radiation is one of the causes of errors in advanced electronic devices, with implications for security and computing technology. Radiation exposure for astronauts. Outside the atmosphere, astronauts are exposed to intense cosmic radiation, which can pose a health risk, increasing the likelihood of radiation-induced diseases. Effects on biology and evolution. Some studies suggest that exposure to cosmic rays may have influenced biological evolution by inducing genetic mutations throughout Earth's history. Production of radioactive isotopes. Interaction with the atmosphere generates isotopes such as carbon-14, used in archaeological dating, and other isotopes that help scientists understand Earth's climate cycles. Cosmic rays are studied using various techniques and instruments. Ground-based particle detectors, such as those used at the Pierre Auger Observatory in Argentina, which measure secondary particles to determine the direction and energy of primary cosmic rays. Space experiments, such as the AMS-02 telescope on the International Space Station, which detects high-energy particles in space, contributing to research on dark matter and the origin of cosmic rays. Underground observations. Laboratories such as Gran Sasso in Italy study cosmic rays using deep underground experiments to reduce atmospheric background noise and improve the detection of neutrinos and other rare particles. Balloon experiments. High-altitude balloon-based experiments allow the collection of data on cosmic rays in regions of the atmosphere where air interactions are minimal. The study of cosmic rays is crucial for various scientific fields. Particle physics. It helps investigate the properties of fundamental particles and phenomena, such as dark matter, thanks to the extreme energies reached by ultra-relativistic cosmic rays. Astrophysics. It provides insights into extreme processes in the universe, such as supernova explosions, black holes, and galaxy interactions. Climatology. Some studies suggest that cosmic rays may influence cloud formation and Earth's climate through atmospheric ionization effects. Space exploration. Understanding the effects of cosmic rays is essential for designing long-duration space missions, such as trips to Mars, to protect astronauts from harmful radiation exposure. In conclusion, cosmic rays offer a unique window into the universe and high-energy physics. Thanks to technological advancements, our understanding of them continues to improve, offering new perspectives on the nature of the universe, the structure of space-time, and the fundamental laws of physics. Thank you for watching. Leave a like and subscribe to the channel to not miss upcoming videos.